Okay, what about now? Yeah, now it's fine. And also here. Here. Also here, test. Yes, oh, pretty, the sound is okay. That's even good. I cannot confirm the quality, but I think definitely be better. Let's see. You're not getting it. I'm not giving it. Smokes. Nice to meet you. Welcome. Yes. Yeah, any problems? So this actually required students are not very many students around to do the exams. I think I'll be enough. So sort of, I mean, we're in 2 weeks time. The semesters are shifted here. We have the following semester. And summer happens. Let's give it a minute. Oh yeah, and are you okay with record with a recorder? Sure. Yes. So we have this. There's a National Institute for Computational Sciences. They broadcast, and I think they also eventually put it on YouTube. That's cool. In fact, I was going to ask for a picture of myself with the background because of the many sponsors, but I'll get a capture from the video. Well, that's no, I'll make a picture because that's the one thing that these cameras are currently not functioning. So your talk is recorded. And I see. Okay. I'll make a picture. Thank you. How much time should I? You have an hour, okay. Maybe a bit shorter in the stuff for questions, but we'll probably, if you don't mind, we'll ask. You can interrupt anytime. So you have an hour. It's going to be very basic, most of it. That's perfectly fine. Yeah, it's from your introduction, your poster. Yes, the invite. There's a lot. Whisper like it's not. That's my issue. I always try to even hear the languages here. I whisper to myself, and I think that my pronunciation is perfect. You don't have to say it out loud to someone else and just feel it. Yeah. Okay, well, I think let's just check. Two bars. Okay, there's. Okay, so yeah, you can use these controls. The keyboard, okay. Please, this is not good. Perfect. Okay, so welcome everyone to the MITP seminar. So today we're very happy to have Adrià Delhom from Universidad Complutense in Madrid. He's here for a few other things. He'll be traveling also to UCT, and you're here for, well, you can maybe explain yourself. To us, he'll talk about toward probing the QFT vacuum entanglement.
Thank you, Tom, for the introduction and for the invitation to speak here. Well, in fact, I contacted you because I was suggested by somebody else who invited me for this SACS meeting, the South African Gravity Society conference that's taking place in Paris this week.
Paris.
So, okay, the idea is basically to discuss this is work in progress. We still don't have any paper out on this yet, but it will come out soon. And it's about probing entanglement that the entanglement structure that is present in the vacuum states of quantum field theories. So first I will motivate a little bit the framework and the problem, then I'll give a pedagogical introduction to vacuum entanglement and what I mean by it, why it's physically relevant, and so on. And then I'll discuss some systems that should be able to experimentally test in the near future, hopefully. So, okay. So first of all, what is quantum field theory? Probably everybody knows this, but some people might think more in particle physics terms or very fundamental terms. The way I understand quantum field theory is as a framework, which is valid across many scales and different physical phenomena. First of all, we have fundamental particle physics, which deals with quantum field theory in the weak field regime usually, and there are perturbative computations for interactions, and it works very well in describing most of the observations that we have of nature at a fundamental level. But also, quantum field theory can be used to describe collective phenomena in condensed matter systems, which are not so fundamental, but the framework is still very good description of phononic excitations or spin waves or any other things like this. Then we can also deal with particle physics related topics, but in a strong field regime, where we have classical field backgrounds, which are strong enough so that the vacuums, the vacuum states are maybe not well defined, or they start doing funny stuff like creating pairs out of nothing, which happens in the Springer effect, or also when we put strong gravitational fields like around black holes or expanding cosmologies and so on, which basically deals with quantum field theory in presence of external classical sources. So for me, quantum field theory is basically a framework that it's useful to describe all these phenomena and probably some others. And then there are some weird properties about the vacuum states of this theory. So there is a very nice theorem by Adrià Delhom, which is, I think, pretty fundamental, which states that in quantum field theory, any two regions of space-time, no matter how separated they are, whether they are space-like separated or not, how big, how small, it doesn't matter. If you take into account all of the degrees of freedom that are localized within those regions, they will be entirely lawless. Okay. I will maybe after the introductory part on vacuum entanglement, the meaning of this will be a bit more clear. But okay, infinitely many degrees of freedom, that's sometimes hard to handle. However, it has been recently shown that one can also find entanglement between localized degrees of freedom in space-time. However, it's not so easy to find it. It decays quickly with distance, and the amount of entanglement between localized degrees of freedom dilutes way faster in higher dimensions, and there are some properties that have just been revealed, can be affected by curvature and so on. So the idea would be, can we actually test any of these aspects of the quantum vacuum? So first, as I was saying, I will give a pedagogical introduction to what I mean by vacuum entanglement, and then our ideas on how to possibly test this. So I will start with simple quantum mechanics, okay? Finite number of particles. We all know the classical vacuum is basically empty, nothing happens, and I would say it's quite boring. But then we all learned that the quantum vacuum is basically not vacuum, in the sense that there is 0-point motion, there are fluctuations, there is 0-point energy, and so on. Take, for example, a harmonic oscillator. So you all know that the expectation value of the Hamiltonian or of the square of the positional momentum operators is different from 0 even in the ground state system. The question is, are there any other quantities with non-trivial behavior? Well, the first thing that I want to discuss is two coupled harmonic oscillators with this specific setting. So the spring constants and the masses are basically the same. For the 2 degrees of freedom, the Hilbert space is the tensor product of the Hilbert spaces for each individual mass, and the Hamiltonian is given by this. So you have the Hamiltonian for the harmonic oscillators and the couplings. The question is, and I'm asking you guys, is there any entanglement in the vacuum state of this system? What would you, anybody wants to reply or has an opinion?
Yes, of course.
Okay, so maybe you know already we'll talk.
I think it's just like you tell yourself one of the masses, the other mass is not going to be in the pure state.
Yes, exactly. So anyway, so I said that it was going to be very introductory because I want to motivate you, but maybe it's too obvious. Well, I mean, to be honest, the question is ill-posed. Because I cannot say whether there is entanglement or not if I don't specify what degrees of freedom I'm talking about. Okay. So first of all, what is the vacuum state of this system? We compute the normal modes. We are all familiar with them. You have the one in which the two masses oscillate with the same in the same direction, and then the ones in which they oscillate in the opposite direction. Okay. They are described by different characteristic frequencies, and then the Hamiltonian is diagonal in terms of this normal mode. So basically, the Hamiltonian in terms of these guys becomes two decoupled harmonic oscillators. That means that the vacuum state or of this system is separable in terms of these degrees of freedom, and therefore, is there no entanglement? Well, as I was saying, the question is ambiguous because then we have to ask what degrees of freedom are we discussing. We need to specify subsystems and bipartition on the Hilbert space, and then we can talk about entanglement. So normal modes of the system are not entanglement because the vacuum is a separable state in terms of these degrees of freedom. But if you try to write this state in terms of states for each of the side Hilbert spaces, then you can easily see that it's not a separable state. That means that there are quantum correlations among the two masses. Okay, so this is not a weird degree of freedom that I'm making up, it's just a very physical degree of freedom. If I look at either of the masses, I will see quantum correlations, even in the vacuum state of the system. In fact, when compute, this vacuum state is basically what's called a two-mode squeezed state between the two oscillators with squeezing intensity that has to do with the ratio of the two frequencies of the normal modes. And you can compute the entanglement entropy between these for any of the two reduced density matrices, and you basically will get this number, which is different from 0. It doesn't depend on the parameters because basically the way the setup is made, they cancel out. So this is what you get in general. And this shows that indeed, as you were saying, the two masses are entangled. So lessons, which maybe are again trivial. There are different ways of decoupling systems into subsystems, and entanglement is not a property of a state, but a state and a bipartition, or a tripartition if you want to call it a tripartite, and so on. And also couplings induce entanglement. Okay, so probably you guys all know this. Now we are progressing towards a quantum field theory and discussing vacuum entanglement there. So first, we basically extend our system to consider infinitely many degrees of freedom, but still discrete. So we consider a one-dimensional lattice field theory with basically the same Hamiltonian, where now the coupling that before was the spring constant is encoded into this guy. I chose to write it like this because then it's pretty obvious that this becomes a derivative operator. So again, the normal modes of these systems, they are discrete Fourier modes. So you take the chain and then you compute what momenta are available. And you realize that these normal modes, they are linear combinations of all the side modes, basically. So they are global modes of the system. And of course, they are normal, so the vacuum basically, you can think of it as a tensor product state, and they are not entangled again. However, if you define local modes in this subsystem, you can see that all of them will have mixed reduced states, which means that they are entangled with the rest of the system. How do you define these local modes? Well, you take all of the site operators for the field and the momentum, and you take these two functions. This hat shouldn't be there, sorry. And you can think of these functions as basically weights, which specify what linear combination are you talking about to define your single degree of freedom. There is a condition that they should satisfy, which is that the sum of these products should amount to 1. Why? Because then the commutator of the two guys is the canonical, you don't satisfy the canonical commutation relation. If, as long as this condition is satisfied, then these guys defines a single mode subsystem of our lattice field theory. For instance, you can take any of these combinations. You see that the square of the sums doesn't amount to 1, but if you consider only the ones in which the support is shared, then the sum is equal to 1. You can think of these guys as smearing or wave functions. Okay. And then I introduced this lattice field theory because these are the way I'm defining localized modes and so on. It's what I'm going to transfer to quantum field theory. Yes.
In this slide, what is the interpretation of this constraint FIGI?
So if you take the commutator between these two guys, basically you will have some ij, Fij, commutator of phi I, phi j. That is a delta because they are canonical degrees of freedom. They are the side position of momentum for the lattice, and therefore you get a delta. So it's ij here, ij, delta ij. So you get that this commutator is missing the I, that is I times the sum of Fij delta ij. So basically you get this. Unless this is equal to 1, this is not a canonical pair. And I want to describe a canonical degree of freedom. So that's why you need that constraint. What's funny here is that, for example, you can take the same function for Q, but then build other function T for different T's, and they can still define a canonical degree of freedom here in Q. So there is a lot of ambiguity here in how you define local modes. Because then what's relevant is only the overlap actually between the functions. Okay, so now field theory. Our coupling with the spring terms now becomes the gradient operator in our Hamiltonian, but then this is a standard Hamiltonian for a field theory. So we all know that normal modes for these theories are basically plane waves. So they are global. So we wouldn't have access in any experimental situation. And they are not entangled in the vacuum state. And this is simple to see. You decompose the field into normal modes, and then your Hamiltonian is basically just a sum of Hamiltonian for each of the individual nodes. However, again, I can define local single modes for the system that we define through smeared field operators. Okay, so our quantum fields, they are distributional operators, so they are not well defined, acting on states and so on. But then, if you take functions of compact support in any region of spacetime, and you consider basically a basis function of compact support in a compact region. If you take all of the smeared operators with respect to a basis of functions of compact support, basically you are taking a basis of solutions for your field theory. So now you take your smeared field operator, you also smear your momentum operator with possibly another smearing function. And again, you can compute the commutator, and you will see that because the commutator of these two guys is a Dirac delta, then again you get that the integral of these two functions has to be equal to 1 for this degree of freedom to be canonical.
And sigma is space-time surface?
Yes, yes. So exactly. So sigma is a Cauchy hypersurface, and then F and G are basically functions of compact support within that hypersurface.
So this is equal time commutation.
Yes, exactly. Yes. Yeah, everything in this slide is formulated in a slice.
Should I worry about the noise in games?
I don't think so. I mean,
There's a volume, it's a volume of space.
yes.
So, is there a problem here?
I think if you choose another parameterization, another slicing of your space-time, the full construction will still,
This is the QFT of the piece of problem.
yeah.
Problem.
So basically, I'm assuming that the space-time is globally hyperbolic, so I can foliate it. And then I can build, once a foliation is chosen, I can canonically quantize the quantitative theory, but, you know, a change of foliation will induce a, you know, a different quantization, but in the end, the physics, will agree. That's the assumption that's made here, so yes, I'm assuming globally hyperbolic.
This is not true for all manifolds.
No.
So there are certain manifolds where you cannot do this type.
Yes, yes, but globally hyperbolic, they are always, I mean, it's always possible to foliate globally hyperbolic space.
Your colleagues are by manifold, which is not different.
Yes. Okay, so of course, for this to define a canonical degree of freedom, at least there should be some overlap. This is, I tried, you know, I'm not the best drawer, and this is what I try to convey here. And then again, the integral has to be equal to 1. So basically, what we get is that we were getting before is that the structure of the entanglement structure of quantum field theory, even in the vacuum, can be very rich and intriguing. Entanglement between localized modes can be found. It has been seen that single mode entanglement, in the sense of this compact degrees of freedom that we're discussing, becomes sparser as we increase the spatial dimension. However, multi-mode entanglement, so if you take subsystems made of a lot of modes, it's rather generic. And also, it has been seen that the amount of entanglement varies between, I mean, with the distance of the subsystem, with the spatial or space-time curvature, and so on. So there are interesting questions that, I mean, and predictions that in principle should be or could be tested. Now, yes.
Sure, it's rather technical question. Let's think about entanglement between localized modes. You have two regions that don't have common like overlap between their past line curve. Do you still see?
So if you take if you take all of the modes,
Yeah.
In each of the regions, so you take all of the a basis of function of common support in each of the regions, and these are the two subsystems. Yes, this is the Reich-Leader theorem.
Looking here, you should think about that. Right? So we're looking
No,
at
these theorems have more general application.
No, it's specialized because you're saying you create a system in the global ground step. You see that's the thing that you're calculating in. So this means that basically, you know, these points that you're looking at, they think they whatever. There's enough time. Yeah,
That's an interesting discussion, I think. But yeah, I don't know how it would be in a space-time which, for example, is expanding at some point but not being able to do it. But I think there is still a quantum correlation within the subsystem, even if they have not been able to talk.
But it depends on your entanglement is defined relative to the state that you've prepared.
Yeah.
And when you say you've prepared an infinite system in its ground state, it means that you've had enough time for each point in that system to talk everyone.
So there has to be some total contact in part.
Yes.
The problem is that I know the theorem in Minkowski space-time, so there's no evolution there.
Yeah.
Maybe, yeah. I don't know how general it is. Might be more general than that, but I'm not sure. Okay, so the question is why local degrees of freedom? I know there's a lot of discussion about entanglement of regions and so on, but why am I choosing local degrees of freedom? Well, first of all, because all experiments that we can do are local, so we will never be able to access global modes. Unless our system is finite, then we will be able to access it, but it's not the case today. And second of all, because normally we have finite resolution, which means that we can only access finitely many modes, yeah, you can only access finitely many modes in general. So basically, this is an idea of I have a detector, I pixelize whatever I detect, and then I get some kind of lattice of degrees of freedom, and then I will get a system of finitely many degrees of freedom with compact support, and then I'm interested in the physical properties. This figure is credited to Adrià Delhom, who recently defended her PhD thesis. And then the question that motivated this work is, can we actually experimentally probe any of these predictions, or will we never be able to do it? So, okay, this is a quote by my former head of state meeting. I challenge you to decipher it. But basically, it's trying to say that we'll do the best it can. Okay. He left many of these funny quotes with us, and I like to quote him. So now a proposal to probe all of this vacuum entanglement business. As far as I know, there is no proposal yet, so all of these are theoretical studies. So the idea comes basically from analog gravity. I've been working in this field for 3 or 4 years now. And then analog gravity is basically the idea that you can simulate field theory in curved spacetimes. And your curved spacetime basically come from a background flow in a fluid system. There are many other systems that also reproduce this setting, but the original idea was in a fluid. And the observation is that pressure waves, so basically sound, in an implicit barotropic and irrotational fluid satisfy a curved Klein-Gordon equation. Okay, this was work by Unruh and Visser. Well, Visser basically rediscovered this idea. And then the curved Klein-Gordon equation is dictated by a space-time metric, which is completely specified by the speed of sound in the fluid and by the local velocity of the flow. These spacetimes that can be generated in this way include expanding universes, black holes, ergo regions, and some others. And there are already experimental realizations, observations of famous phenomena like Hawking radiation, superradiance, particle creation, expanding universe. And people have been trying to basically measure entanglement from per production phenomena for some time. There are some claims that have been disputed and so on. But the idea is I was working on this and I was like, okay, so if we have the techniques to probe entanglement in these setups, why are we not probing the simplest one, which is basically a homogeneous fluid in cosmic spacetime, and then there I have a vacuum field. So that was general field theory, but now how do we do quantum field theory? Well, we need systems with very low temperatures because otherwise everything will look pretty classical. So now we go to things like Bose-Einstein condensates, quantum fluids of light, and probably there are other systems that can satisfy this, but these are the two that I've been working with most. So these are generally described by a constrained complex field that creates and destroys microscopic degrees of freedom. Okay, so you take your field psi, you decompose it in momentum modes, and then you say this creates an atom. Well, psi destroys an atom with momentum k, psi dagger creates an atom with momentum k. And when I say constraint, it's because psi dagger is the conjugate momentum to psi, exactly like that, as happens in the Schrodinger equation. Okay, so this is a generic definition. And then the idea of quantum fluids, or one of the ideas behind the formalism, is that there is some whatever quantum state which has macroscopic occupation numbers. Okay, so I can do a mean field theory description of this system and then compute some quantum fluctuations around it. So for the mean field theory, I just take the expectation value of the macroscopic field operator, and I get some background classical field. The equations that this background is satisfying can be seen to be derived from this Lagrangian, okay, which is the Gross-Pitarski Lagrangian. It's basically a nonlinear modification of the Schrodinger Lagrangian. And you can describe this complex field in what's called the density phase representation or Madelung representation, which is basically a decomposition in terms of a density on a phase, okay? And then when you write the equation of motion that you derive from this Lagrangian in terms of these two variables, then you get something like a continuity equation and an Euler equation, where the velocity of your fluid is the gradient of the phase. Okay, this is pretty general. And then one can ask, okay, what happens now if I consider linear fluctuations of the density on the phase on top of this background? Okay, so you go to the Lagrangian, compute the second order expansion in terms of these perturbations, and you get that Lagrangian over there. From that Lagrangian, you can see if you compute the momentum conjugated to phi, which are the phase perturbations, it's actually the density perturbations with a minus sign. So that means that they are not independent degrees of freedom, but a canonically conjugated pair. This is basically coming from the fact that the theory is a constraint theory for a complex scalar field, so it's one real degree of freedom. But we have described here. So now, if it's a conjugated pair, well, you can, derive the equation of motion, and you can see that if you rewrite the equation of motion in terms of phi of the phase perturbation, they satisfy some sort of generalized Klein-Gordon equation which has that specific form. So you have the Klein-Gordon operator with the characteristics given by the speed of sound, and then you have a previous operator multiplying the whole thing, which is basically an inverse of a derivative operator. This is a length scale, which is basically controlling the length scale at which interatomic interactions start being relevant. So the idea is that in this field description, in the ground state, we assume that most of the microscopic degrees of freedom are very slow, and they don't get too close to each other. So everything is described in terms of the S wave scattering length, and the thing is also, you can describe it with the weak coupling and Born-Oppenheimer kind of approximation. And then basically for lengths that are longer than this ceiling length, the system is well described like this. So the idea is you consider only perturbations that are long wavelength with respect to the ceiling length. So basically they have to satisfy this. And this is some sort of relativistic limit for the above equation, because then you just get the Klein-Gordon equation. And this is what is commonly known as the phononic description of density and phase perturbations in fluids and quantum fluids in particular, where the causal speed of propagation is this speed of sound. Okay, everything is given in terms of the interaction strength of the microscopic degrees of freedom and the density of the background flow, and these are the relevant parameters. So now we can also consider, well, we can basically quantize the linear fluctuations, or which is the same, consider fluctuations over the mean field. They are well described by quantizing our linear perturbations to density and phase. We then impose a canonical combination relation between these two guys. Notice that I shifted this is the momentum and this is the field because there was a minus sign. Okay, so I'm just saying it because maybe some people are confused. And then we define localized modes within whatever condensate I'm doing, again with function for support. Now I decided to use the same function for the two degrees of freedom for simplicity. And then what we verify is that the integral of that function squared must be equal to 1. Okay, then this pair defines a canonical degree of freedom. So we now take two modes defined by the smoothing functions fa and b. They can be at whatever distance, they can have whatever spread, and so on. And then we assume some vacuum or thermal state for our quantum field, which are basically these fluctuations of the mean field for density and phase. Okay? Since these are both Gaussian states, they are fully characterized by the mean and the covariance matrix, which is basically the first order expectation values and the second order expectation values. 1 and 2 point function. The mean is usually 0, and we have some correlation matrix. This is the covariance matrix for the two subsystems, where these two guys basically are given by the 2 point functions of field and momentum squared for each of the subsystems. And this is encoding the correlation between the field of 1 degree of freedom and the other, and momentum and the other momentum. And then the zeros here, they are zeros because I'm assuming thermal or vacuum states. In other states, they don't need to be 0. Okay, but if we are assuming that we work in the setup, which is actually normally accurate in expressions, they have whatever DC or whatever polarity fluid at some given temperature, and normally the state of the field that you have by computing these fluctuations is a thermal state at the temperature of the system. Okay. So Yes.
The same as the function.
Yes, these are the meaning functions. So they only need to be of compact support. That's the and normally what the degree of smoothness. Normally you want them to be at least as smooth as your differential equation require, but you can also have smooth not smoothness but differentiability. You can also have smooth functions of compact support, and F and these F A and B, they need to be whatever functions, and they need to satisfy this concept, but yes, these are the fundamentals of that. So, okay, we've seen how in a condensate or a quantum fluid, we have a natural implementation of a quantum field theory, in which in principle, at least in other setups of experiments, people have been trying to access the entanglement content in those field degrees of freedom. So the idea is, can we actually test the entanglement between these local degrees of freedom in a condensate? So I was saying most of the techniques are already developed, even though here we want to deal with simpler setups. So a stationary homogeneous fluid would lead to a quantum field theory in a Minkowski spacetime with some boundary normally because the system are finite. Inhomogeneities or time dependence can generate spatial or spacetime curvature, so universe expansion or whatever black hole you want to engineer, or maybe a secret universe. Things like this have been engineered or simulated in laboratories, and then we can again test the different dependencies of that have been predicted. And what we need to be careful about is that the effect of temperature must remain very controlled, because temperature quickly extinguishes the entanglement. So as I heat up a system, the entanglement between degrees of freedom is lost, and it's not that it decays, but at some point it completely vanishes. Okay. So we need systems with very low temperatures. That's why we go to quantum fluids. Now, I'm going to show now some preliminary results with some of specific Smiling functions that we are choosing because they are convenient in terms of analytic tractability. And then I will I will show you how we actually do get entanglement for these functions of compact support in Bose-Einstein condensate systems, with parameters that have been used in recent experiments, and also assuming some errors, we will see that in principle it should be the best job. So first, the Smiling functions. So I'm going to do 1 and 2 dimensional, effectively 1 and 2 dimensional condensates, which means that you take your condensate and you squeeze it in one direction, so you have basically a plane, or even squeeze it in another direction and you have basically a spaghetti. And then the transfer degrees of freedom are basically completely trapped, and you only excite degrees of freedom for the photonic field in one of the direction or two of the direction. So these are basically the Smiling functions. I'm going to consider a ball in the center and then shells around that ball. Okay, so these 4 lines will be different balls with different bigness and width and smoothness. So delta basically is giving you the smoothness in the transition, differentiability, sorry. And then the shell around the ball will be 0 in the ball, then it will have a bump and it will extinguish them. Okay? This is valid for 1 dimension and 2 dimensions. So I consider here, for example, the ball, and then this would be a shell, this would be another shell, this would be another shell, etc. In 2 dimensions, this would be the ball, shell, then another shell, and so on. And then the subsystem that I'm going to define is not each of the degrees of freedom of the subsystem, but if I use I use 2 colors for the 2 subsystems. So in this case, for example, I'm considering the ball and the second shell as one subsystem, and the first shell as the other subsystem. And I'm going to compute entanglement between subsystems. Okay. Okay. So in 1 plus 1 dimensions, for different numbers of ball and shells, this is the prediction that we get for logarithmic negativity. We are using this quantifier because it's useful even when subsystems are in a mixed state. And what we see is that we can observe entanglement between 5 nanokelvin and 20 nanokelvin for different amount of balls and shells. So for a system that is composed of only 2 degrees of freedom, it dies very quickly with temperature. But as soon as I start increasing the number of degrees of freedom in each of the subsystems, you get more and more entanglement. It might saturate and probably it will diverge, but slowly. We have not computed too many. Okay. And then those are the results for 2 dimensions. More or less can be seen to be similar. Maybe a little bit less entanglement. This is again logarithmic negativity. And then considering n equals 1 is ball and shell, n equals 2 is ball, shell, and another shell, and so on. Okay, so again, as I increase the number of shells, I get more entanglement, and then it dies off higher temperature.
So what are in the temperature in that?
Because this is the range. This is the best that condensate experiments have been doing. I mean, there are even 0.0 something nanokelvin in some experiments.
So what are the materials?
Normally, they are atoms, atomic systems, that have some bosonic quantum state that you can drive the system towards. And basically, what people do is normally they cool all of the atoms by evaporative cooling. I think they do some stuff with the laser, and then basically the atoms that move too fast, they fly away from the system.
Yes, but I was just asking is what parameters that you use. Why not say something? No, if you use realistic parameters, you would get the well.
Yeah.
But in some system, like what atoms are you using?
So rubidium, for example, is one of the materials.
Your calculation, what parameter?
I don't know the species, but I know the healing length is of the order of micrometers. The temperatures, we can put whatever we want, but they are in the experiments of the order of nanokelvin.
Or what are the parameters? It's the healing length and
The speed of, so basically you have the density and the interaction strength, but normally people discuss more in terms of healing length and then the sound speed.
Okay.
And
you just do typical parameters.
yes, so basically
Like
the thing is that we did a work in which we were so there is an experiment in Heidelberg where they simulated an expanding universe, and they observed perturbation between phonons from the expansion. Okay, and our idea was, can we measure the entanglement generated in this perturbation? So we did a work, and we showed that it should be possible with a mild improvement, basically changing the type of expansion. And then when we realized that we took similar parameters to what they had, but we assumed now that we have a flat condensate with zero evolution, and the parameters that we are playing around with are similar to the best that these people can design. And this is basically cutting edge from what I've been.
I'm trying to understand the thinking calculation because it's you just working with ozone vacuum.
Yes.
So what makes this calculation tricky?
I don't think it's tricky.
Okay. Okay.
I mean,
So what do you calculate? You calculate like
yeah. So basically, you compute these guys for whatever state, a vacuum or thermal state, for these degrees of freedom. Okay, and then the tricky part might be you might have to do some Fourier integrals and stuff like this, which are highly oscillatory. But this part is Patricia doing it. She's an expert on all these computations because she has been dealing. She's one of the people that have been computing entanglement between localized degrees of freedom in vacuum in the vacuum computer. So she has all this machinery under control. But I would say this is the most tricky part because the rest is just Gaussian state formalism and everything is very straightforward. And then when you increase the number of degrees of freedom, of course, the analyzing can get expensive, but it's only a matter of doing.
yeah. So you're doing something like log of reduced installation. So you're trying to log of reduced installation.
Yes. Yes. So
But you probably. So in principle, you have like very high creation rate numbers and stuff. Like you probably truncate all these series
So for us, we compute these 2-point functions, and the reason why we are choosing this specific form of this meaning of this meaning function is because Patricia found that this can be the Fourier transforms of these guys can be computed analytically. That way we can have under control what those numbers we are looking for because we want to remain in this relativistic regime. So we want to be, we don't want these meaning functions to have wavelengths that are smaller than the meaning length. And then we are using those because you can analytically compute the 2-point functions and the Fourier transform. And then from that you get the covariance matrices. You multiply with the symplectic form, you diagonalize, you find the symplectic eigenvalues, and you compute the logarithm activity.
Oh, it's just that, just with, okay.
Yes.
I just asked, I want to go, but I just wanted to ask.
Sure.
In this case, this is states.
I don't know. I mean, they probably are. They probably are because it's what what you get in general. But I have not computed them. The state itself.
It's not about the use mistake, it's just based on some degrees of freedom.
Yes. So I would say that probably there should be some squeezing in some abstract sense, but I don't know what type of squeezing because so what I was discussing before is a 2-mode squeeze state because there are 2 degrees of freedom. If you get more, then the transformation is bigger. So in any case, for sure, there will be a transformation within the symplectic group of all of your degrees of freedom, which is not part of the orthogonal group. And this normally you can associate with some degree of squeezing in some high dimensional space, but I am not familiar with squeezing operators in very high dimensions. I don't know if people use them like that or are defined like this, because squeezing, I think, the term comes from a quantum optics. Single mode squeezing is very well known, 2-mode squeezing as well, but high dimensional, I'm not sure if people use the term.
Then how do you get physical heavy states?
He's using the thermal state. Yes, he's using the thermal state. That's it. He doesn't produce a state. It's an experiment. I think it's just properties of the thermal state.
Yeah. So I'm assuming that the system is in a thermal state because that's what you have in an experiment. You have a BC at some Kelvin temperature, and then your fluctuations can be seen to agree with the quantum field theory at that temperature. And then I take those subsystems with degrees of freedom and compute the new density matrix, which is equivalent because the state is Gaussian to computing only the covariance matrix, so 2-point correlations and 1-point correlation. That's it. And then, okay, so these are the results. Basically, the idea is, yes, with available parameters, with available experimental systems, we can find entanglement between localized degrees of freedom, and in principle, we should be able to test these predictions. And just to finish, we also assumed basically a 5% relative error in the entrance of the covariance matrix. We assume this number because this is what they report in this high-level experiment. They also compute density matrix, covariance matrix elements of 2-point correlation functions. They just don't to compute them all. They don't do tomography. I don't know if they were not aware that they can do it with their system or what. But they report around 5% relative errors in this element of the covariance matrix. So we basically assumed something like this, and then we are plotting 3 sigma contours around the lines, and we see that in principle, the best temperatures that people can get now are of the order of 10 nanokelvin with this parameter range. So we see that if you increase a lot the number of degrees of freedom, you are more or less able to distinguish at 3 sigmas. Probably a lot of degrees of freedom is too large for the system because then at some point you grow out. So we should be working safely at around 3, 4, 5 degrees of freedom. But you can see that still, if you go with a little bit less confident, which is not so uncommon in these contact matter experiments, in principle you should be able to detect, or maybe with a slight improvement, you should be able to detect. So outlook. The structure of the vacuum in quantum field theory is surprisingly rich in entanglement. Maybe not so surprisingly, I don't know. There are entanglements between localized degrees of freedom in the quantum field theory vacuum. This entanglement can be affected by curvature of dimensionality, which has been recently proven. If we want to test all of this, we require systems with very low temperature because the entanglement quickly degrades as you increase the temperature. And we've seen that quantum fluid platforms can be very promising as probes for this structure of quantum field theories, mostly because they are they are operating at extremely low temperatures, and we have a natural quantum field theory built in from these hardwares. Maybe if you want a technical downside is we are not sure on how we can do full state tomography in stationary states. So we are thinking about possibilities right now. There are some of them, and another possibility that we are thinking of is basically maybe implementing some expansion, and then if we are able to prove that the expansion doesn't produce entanglement between these local degrees of freedom, then it might be a way of allowing to do tomography, because once you have expansion, there is no method to actually do it, because we did in our previous paper with expanding. So, thank you all for listening, and I'll take questions.
Same question.
So it's about the stars, about topography. So suppose I'm not expert on those assessments, but it's if I want to do a tomography of the BEC state, yeah, it's already quite challenging. You've got another level of difficulty on top of it because you want to do tomography of this specific density matrix that you define with this F function. Do you have any idea whether there's I mean, it might not be very realistic at this stage, but do you have like experimental?
No, it can be done. It can be done. So for example, for the Hawking effect in analog gravity, there are ways of doing it because there are some approximations you can make. You can see that some elements of the matrices are not relevant, and the rest you can compute and measure. For expanding universe, you can also do it because you get a temporal dependence in the two-point correlation because of the expansion. You get some coherence in the phases of the different modes, and then from basically taking time derivatives of the two-point correlation, you can find you have the two-point correlation that you can measure is momentum, and then by taking time derivatives, you can measure field and field momentum. Okay. The problem in stationary state is that there is no time derivative to take, and we have. One of the proposals would be do a little bit of expansion. Then we need to check whether the expansion creates entanglement between these local degrees of freedom, which there are indications that it will not. And then that allows you to compute the evolution, or at some point quench the BC through a phase-back resonance. You can make the interaction coupling go to zero. Then you're basically getting a pre-evolution for the atoms, and apparently you can convert momentum correlation into field correlation at a later time. This is another idea.
Okay, so the idea is to measure in the BC the two-point functions accurately enough, both XX and BP, and
yes,
and then after you've done that, yes, you can post-process and figure out all these.
Yes, and this can be done. I mean, measurements of the field of the density fluctuations. That is. Basically, they are destructive measurements, but you do a lot of statistics and you can reconstruct more or less the distribution. For the phase fluctuations, it's more complicated. As far as I know, there is no clear measurement of phase fluctuations. But if you can compensate with time evolution somehow, then you can get them for the density fluctuation. Okay. And this is doable today.
Any other questions?
This you said there are two parameters. One is that the speed of sound is it corresponds to speed of light. Right?
Yes. Yes.
What is this healing then?
So the thing is that here you don't have a smooth, a completely smooth background structure like in standard quantum field theory, because your background spacetime is the mean field for the atomic system. So that mean field you can see it as a continuous field as long as you don't resolve your space so much that you start seeing the shape of your atom. If your atoms still look delocalized somehow, and if you don't look too close, then your background looks like a continuum. But if you start looking closer and closer, at some point you will see the discrete structure of your atomic system. So you can think of this healing length as the length scale at which the interatomic interactions or the properties of the atomic degrees of freedom start to show up in dispersion relation, in energy computations, and so on.
Also, by the scale where you
Yes.
the theory breaks down.
Exactly. So imagine, for example, you have some kind of breakdown of Lorentz symmetry because you have a discrete spacetime at the Planck scale. So it's the analog of that scale. And you can also, from this equation, from this modified equation, it's not complicated to compute a dispersion relation. Basically, you get a supernominal line, which is quartic in the momentum. So you get k squared plus k to the fourth inside the square root. And the k to the fourth term is basically controlled by this guy. Maybe it's not so obvious that you get a fourth order because you have the inverse of this operator, but you can go to the Hamiltonian system and then get the dispersion relation. So basically, what you get is a relativistic dispersion, a low case. So a dispersion which is linear in k, and then at some point it starts curving, and then this point is controlled by this scale. Basically, it's a when k is 1 over this guy, more or less, you start seeing the dispersion. And when you go to very ultraviolet case with respect to this guy, your dispersion relation is p squared over 4. So the non-relativistic are all in this way.
Let's think out it again.
Thank you.
Oh, so,
Subject.
oh, there's a chat.
Oh, okay. Okay.
Okay, let's then think again. Good talk. So one of the things we're also trying to verify here, for example, is this really shader.
Not really,
or-
because that involves necessarily infinitely many degrees of freedom in our region. So, but one of the things I would like to see, for example, so if you test all of this structure of entanglement between local degrees of freedom and you see that predictions are, I don't think there will be any deviation because it's very basic. You see, if this is wrong, I mean, everything else could be so. But what would be interesting to me is to see, for example, if I start considering denser and denser subsystems in terms of degrees of freedom, and so, like, how do I recover this theorem from a discrete version that I can, take the continuum limit from?
Yeah.
The problem is that this problem looks pretty hard computationally speaking, because you have to diagonalize crazy matrices. Yeah.
When I was even like, what brought you to South Africa?
The SAGS meeting,
What's that?
the South African Gravity Society.
Oh, okay.
Yes.
Okay.
So my training is actually modified gravity and so on, and metric affine theories and gravitational theories. And then I started doing analogs, and then I thought, okay, we can also test these things about KFTs, which are not related necessarily to any gravitational idea, but at least relativistic. Yeah. Thanks.
I saw a map of Africa with Southern Africa something in the beginning. So what was that thing? Southern Africa.
Okay, so basically, I'm getting many sponsors for this trip
Oh, okay.
because there is several people funding because
Funding your trip. Too.
yes, slightly funding.
So all these people are funding your trip.
So some of them are my employers.
Oh, okay.
Okay.
So embassy is
This
funding.
is the embassy because
Yeah.
they pay me some 300 euros.
Oh.
These are my employers.
Okay.
These three.
Okay.
Okay. This is some foundation related to maybe embassy